Good morning, everybody here in New Mexico to the Planetary Sample Seminar Series. Good afternoon to those who are east of the Mississippi. And of course, good afternoon to those who are across the pond. But thank you guys for joining us so much today. We have Dan Moriarty from the Goddard Space Flight Center with us. So Dan is an assistant research scientist at NASA Goddard through the CREST Cooperative Agreement at the University of Maryland. His research and other duties involve integration of remote sensing data from various instruments. He's a member of NASA's Sparks SDDT and is the South Pole Aitken theme lead for RASL Survey Team. So Dr. Moriarty also contributes to several NASA teams supporting the Artemis program. And today he's going to talk to us about sampling at the South Pole and the Aitken Basin material in the Artemis exploration zone. And so Dan, please take it away.
Yeah, very good. Thank you for the introduction, and thank you very much for the opportunity to speak today. I just wanted to note that I really value the survey program, and I personally owe a lot to its predecessor, NLSI, which is a really, really great resource when I was a grad student. So I know that survey is a really great resource for students today, and it's great for these collaborative efforts across different institutions, across different agencies. So really excited to be talking in this forum today. So today I'll be discussing the mineralogical diversity of the Artemis exploration zone. So this includes a variety of things. So how can we characterize that compositional diversity from existing orbital data? And we want to do that with the purpose of optimizing our surface science activities and what some of the science implications from the diversity we observe are. So specifically, we want to understand the likelihood of sampling material from the South Pole Aitken Basin. And this has been one of the highest priority science goals in the previous 3 planetary science decadal surveys. We've yet to send a dedicated mission to do that. We're still investigating things like the Endurance rover to possibly sample material from the interior of SPA robotically. But I think there's a chance we could get some pretty decent SPA samples from the Artemis exploration zone itself. And so that's what we're going to talk about today. Okay. So rock and soil samples that we'll collect through Artemis, they're relevant to a number of decadal level science questions that have been outlined in various guiding documents. I've highlighted a few of those science goals here. But essentially, this gets boiled down into the Artemis 3 Science Definition Team Report Goal 1B. So this is to probe planetary differentiation and evolution processes, including formation of a magma ocean, crust, mantle, and core. So this is a very, very broad goal. This is essentially capturing everything from accretion of rocky planets to full expenditure of the internal thermal energy. So yeah, a lot of very high level science questions involved here. But we know Artemis will provide important new insights to many of these questions. One of the highest priority goals in lunar science is to better characterize the early differentiation and evolution of the lunar interior. So to do this, it would be really helpful to return samples of the lunar mantle. Understanding the evolution of the lunar mantle is certainly a high priority science goal with far-ranging implications. And there's currently no confirmed mantle materials in the lunar sample collection. So our current understanding of the lunar mantle and its evolution is derived primarily from things like geophysical observations, petrology models, and laboratory experiments derived from Mare basalts and volcanic glasses. So a high priority goal going forward is to identify and characterize where mantle materials are currently exposed on the surface. This is a critically important endeavor for advancing lunar science. So our goal today is to integrate remote sensing observations with models of impact basin formation and lunar mantle evolution to identify and characterize the most likely surface exposure of mantle materials. One issue is that in a lot of the recent literature, there's not really great agreement as to what these mantle materials will actually look like from a compositional point of view. So we really want to dig in and understand what we're actually looking for before we can go look for it. So our current understanding is that the differentiation of the moon proceeded from a global lunar magma ocean. So a lot of the details of this process are not completely understood. But the basic idea is that as the moon cooled and crystallized, minerals crystallized out of that magma ocean in a sequence based on its temperature, pressure, and composition. So early crystallizing mafic minerals sink to form a cumulate pile at the bottom of the magma ocean, whereas late crystallizing plagioclase floats to form a flotation crust. So by the end or by the later stages of lunar magma ocean crystallization, we get left with this kind of sandwich of these late stage materials. So they're enriched in things like iron, titanium, thorium, some of the creep elements. Basically, a lot of these incompatible elements are the last things to get sucked up into the last minerals to crystallize. And they end up sandwiched between the mafic cumulate pile at the base of the magma ocean and the plagioclase flotation crust. So of course, this isn't the end of the story, as the internal lunar stratigraphy is expected to evolve through processes like gravitational restructuring and convection. But generally, this cumulate stratigraphy sets up a general framework for understanding the various compositional end members that we might encounter if we're looking for excavated mantle material. So where can we go to test this hypothesis? The general wisdom is as follows: to find the deepest stuff, go to the biggest hole. The biggest hole on the moon, as currently understood, is the South Pole Aitken Basin. So SPA is a vast ancient impact basin on the lunar far side. It's over 2,000 kilometers in diameter. It exhibits a pretty unusual volcanic history, and we have impact models that suggest that the SPA forming impact was so big that it excavated completely through the plagioclase flotation crust and melted and excavated significant volumes of material from the lunar mantle. So these impact models suggest that SPA ejected mantle material. Some recent three-dimensional impact models run by Jordan Kendall show a few examples for likely distributions of those mantle materials on the surface of the moon. So here in this red to black gradient, we're showing one example of a predicted distribution of mantle ejecta around the South Pole Aitken Basin. And so, of course, this early ejecta blanket is then subject to about 4 billion years of subsequent impact cratering. So to capture some of the effects that might have, we've superimposed the distribution of all impact craters greater than about 20 kilometers on top of that ejecta blanket. So the largest impacts, such as the Apollo Basin up here in the northeastern region of SPA, those might have excavated completely through the South Pole Aitken ejecta blanket and removed that material locally. But smaller craters in the maybe 20 to 100 or 200 kilometer range, those might actually just be re-excavating that SPA ejecta from beneath a kind of diluted and mixed regolith layer.
All right, calling me.
Sorry, I think there's an open mic.
Mute the.
Okay.
Okay.
Yeah, can we mute Qingju Yin?
Oh, I'm sorry.
Sorry, thank you. Okay, right. And so the current distribution of mantle material on the surface today, it's been reshaped and diluted by billions of years of these impact and other geologic processes. We can have burial by ejecta from other basins and redistribution through these impact events. So if South Pole Aitken material, if the mantle material ejected by SPA has been preserved at the lunar surface, it should follow this type of distribution. So the initial emplacement in this black to red gradient kind of convolved with this subsequent impact history. So we should see it following a kind of similar crescent-shaped distribution. And so intriguingly, this predicted distribution of mantle material resembles pretty closely the present-day distribution of thorium that's observed in lunar prospector data. So as we mentioned above, thorium is one of those incompatible elements that's present in this sandwich of late stage lunar magma ocean materials. And so it's an important tracer of these late stage cumulates and could potentially serve as a good proxy for the current distribution of this deep SPA ejecta at the lunar surface. So to confirm that, we can look at some additional compositional data to see if there's additional evidence for this thorium being related to these late stage lunar magma ocean cumulates. So here we're showing a collection of diverse compositional data from Moon Mineralogy Mapper and Lunar Prospector. So there's a lot going on in these maps. So we're not going to go into a ton of detail here, but essentially what we're showing is that there's really good correlation between thorium distribution and several other important compositional markers of these late stage lunar magma ocean cumulates. So we're seeing things like iron associated with thorium. We're seeing things like titanium. We're seeing potassium representing some of the creep. And we also see evidence that this is associated with iron and calcium-rich clinopyroxene minerals, which again are predicted to be the primary minerals forming with some of the ilmenite in these late-stage lunar magma ocean cumulates. So all of this compositional data is kind of holding together to suggest that thorium is indeed a pretty effective proxy to understand the current distribution of these deep materials excavated by the South Pole Aitken forming impact. Okay, so intriguingly, it does look like this thorium distribution, while the highest abundance shows up in Northwest SPA, this thorium distribution does extend down to the lunar South Pole. So initially, it seems like we might have a chance of sampling some of this material within the Artemis exploration zone. So let's look at this in a little bit more detail. So here we're showing maps of Lunar Prospector iron on the left and Lunar Prospector thorium on the right for the Artemis exploration zone around the lunar South Pole. So here we've highlighted the location of the 13 original candidate Artemis 3 landing regions. And in this view, South Pole Aitken Basin is to the bottom left of the map. So as you can see, both iron and thorium abundance shows a fairly pronounced gradient from the bottom left to the upper right. So both iron and thorium are highest in the direction of South Pole Aitken, which is what we would expect if we're looking at a distribution of South Pole Aitken ejecta moving away from the basin. So we kind of confirm that here numerically by just looking at a scatter plot. So we see that generally the candidate landing regions that are closest to South Pole Aitken show the highest thorium and iron abundance. So that's pretty straightforward. So already from the Lunar Prospector data, we get a sense that the best place to go to sample SPA ejecta in the Artemis exploration zone would be those candidate regions that are closest to SPA. But there's a lot of detail missing here. So an issue with the Lunar Prospector data is that it's very low resolution. It's low spatial resolution. So we're looking at something like tens of kilometers per pixel. So at this scale, data is not particularly useful for understanding any geologic associations or for planning surface activities to visit sites with high science priority for a sampling strategy. So for a more detailed view, we turn to regional mosaics created from near-infrared spectroscopy products. So generally, these instruments are dependent on reflected solar illumination. So there are some major challenges in using and understanding this data at these highest latitudes where we have really extreme illumination conditions. So we want to make sure we take a few steps to validate anything we're seeing here in this reflectance spectroscopy data. So the first thing I'm showing here on the right, this is a map of an existing Kaguya product from the Kaguya Spectral Profiler. And this is a map of derived iron abundance. So when we compare this iron abundance map from Kaguya to the iron abundance map from Lunar Prospector, we see that there are some pretty similar trends. So particularly, we see that there's an enhancement in iron down in this bottom left quadrant which corresponds to the direction heading towards the South Pole Aitken Basin. So that's in pretty good agreement with what we see in Lunar Prospector. But there are some other issues here that are a little funny. So for instance, we're seeing that there's this really pronounced minimum, local minimum in iron abundance at the highest latitudes. And that's not reflected at all in the Lunar Prospector data. In the Lunar Prospector data, there's a pretty smooth gradient going from SPA to the near side. And that's not what we see in the Kaguya data. So we've looked into this a little bit, and one possible issue we're running into here is possible non-mineralogical albedo effects. So on the left, we're showing a map of the Lola albedo product. That's a really nice product that's essentially just measuring the amount of return on the Lola laser shots. So it's very simple photometry. They've brought their own light source, so it's pretty reliable in that sense. But what we see is that there's an unusual enhancement here at the very highest latitudes, and that correlates pretty directly with this area of very low iron abundance that's reported in the Kaguya product. So this kind of makes sense because this Kaguya spectral profiler data is calibrated or scaled to this Lola albedo product before they derive the iron abundance. And so since iron abundance generally has a large effect on the albedo of lunar materials, think of the differences in albedo between high iron Mare basalts and low iron highland materials. So it's possible that their model is overinterpreting a difference in albedo that at these really high latitudes is the result of some non-mineralogical effects. So if that's true, if this albedo effect is not actually related to mineralogical differences, this could be biasing the Kaguya iron abundance result. So we want to investigate that a little bit further by looking at some other independent data sets. And so first we turn to moon mineralogy mapper data. So generally, M-cube data, we see that, so here we're looking at a map of the 1 micron integrated band depth, which is sensitive to the abundance of these iron-bearing mafic minerals. So generally, the iron abundance maps we're looking at here should correlate with this 1 micron integrated band depth map. There are very different ways of deriving a parameter map. So they use different algorithms to come to a result that should be correlated, but isn't always. So for instance, this band depth map will be pretty independent of the actual albedo of a particular pixel. So this is a good way to check whether or not this effect is mineralogical, related to the abundance of mafic minerals, or if it's something else related to a non-mineralogical albedo effect. Okay, so but generally this 1 micron band depth product is enhanced across the lunar South Pole in the M-cube data. And so there's a few possible reasons that could be. So one is that, yes, there is an enhanced, there is an enhancement in mafic content across the South Pole. Some of this could be due to SPA ejecta. Some other factors could be space weathering. So there are differences in the solar wind flux at the highest latitudes. So the rate of space weathering could be different. So this modification of band depths through time, through space weathering, could be much slower at the pole than it is the equator, for instance. And there's also the possibility of instrument artifacts. So at these high latitudes, you generally have fairly extreme illumination conditions, so that can give you lower overall signal to noise, some interesting thermal component effects, and also some more challenging photometric effects that you need to deal with in your calibration. So all that being said, we've employed a pretty multifaceted approach to understanding the nature of this spectral signature at these high latitudes. So we've compared across M-cubed mission phases. We've compared between several different ways of measuring these mafic mineral sensitive parameters. And we've also done some comparisons to the North Pole and South Pole. Okay, so here we are showing a suite of 4 different spectral parameters that are sensitive to the presence of mafic material. So these include both band depths and integrated band depths for the 1 and 2 micron spectral absorption band that show up when you have these iron-bearing mafic minerals, things like pyroxene and olivine in your lithologies. So a little counterintuitively, we've got the maps for the South Pole up at the top and the North Pole down at the bottom. And so what we see is that there are enhancements in all of these parameters at both poles. But what we see is that the South Pole is systematically higher than the North Pole in all 4 of these mafic sensitive parameters. So this suggests that this observation that we have an enhanced abundance of mafic minerals at the South Pole, that's pretty robust. That's not just a latitude-dependent effect. If it was just a latitude-dependent effect, you would see a similar magnitude at both poles. Since we see that the South Pole is enhanced relative to the North Pole in these parameters, that suggests that this is a real signature related to the presence of mafic minerals. And some of those will be due to the presence of the South Pole Aitken Basin. But you can see that this effect persists across the entire area, poleward of about 60 degrees. Okay. M-cubed also operated in several distinct optical periods. And so in these different optical periods, there were different observing geometries, there were different orbital altitudes, and the detector response on the instrument was actually a little different as it went through kind of big swings in temperature. And so what we see is that across these different mission phases, across these different optical periods, there's evidence for this enhancement in these mafic parameters showing up consistently between these optical periods. So again, this is not just an artifact due to a specific set of illumination conditions. This is something that shows up across the entire mission. Okay. So when we take the M-cube data, we look at these regional mosaics, and then we zoom in just on the Artemis exploration zone. We can see that there are actually a lot of gaps in this data. Basically, the way these regional mosaics were assembled, they were not assembled to optimize illumination from individual images. They just were kind of put together based on a phase angle constraint. So some of these areas where we have data gaps, we'll be able to go fill those in with the full resolution individual images. But for now, this global mosaic or this regional mosaic is a good way to look at the general properties of the area. So again, when we look at this map of M-cubed 1 micron integrated band depth, it's sensitive to the abundance of mafic minerals. We can see again that some of the overall spatial patterns match what we would expect from the lunar prospector and the Kaguya maps. So we see that there's this really broad enhancement to the bottom left of the map, again, which is associated with the direction towards the South Pole Aitken Basin. But one interesting thing we see in the M-cube data, and data is limited at the highest latitudes, just because the illumination limitations. But we do see that there are areas close to the pole where we have some enhancements in these 1 micron band depths, in the same areas where you're seeing local minima in this, the Kaguya product. So this kind of suggests that maybe the Kaguya data is picking up on an albedo effect rather than an iron abundance effect. So it's possibly a non-mineralogical effect here, because again, we see a lot of evidence for deep absorption bands, or at least non-zero absorption bands here. And so, yeah, generally at this scale, the distribution of mafic minerals and iron in the M-cube map is a bit of a closer match to the lunar prospector map than the Kaguya map. And something that my close colleague Noah Petro sent to me yesterday, there's a really interesting new result from the class X-ray spectrometer on the Chandrayaan-2 instrument, which is showing an enhancement in iron in this area that's associated with this crater Ibn Baja. And so that shows up in 3 different orbits from Chandrayaan-2 class instrument. And we see that correlates really well with an area of enhanced iron or enhanced mafic mineral abundance in the M-cube data. So there's something going on here. Maybe this is a high latitude Mare basalt, which we haven't really seen much evidence for previously. But this is certainly something worth looking into, the possibility of sampling Mare basalt at very high latitude. There's at least something very iron rich here that seems to be showing up in multiple independent data sets. So certainly something worth pursuing. Okay, but so far, as I mentioned, we've been showing data from this M-cubed global mosaic, which has limited data availability at the highest latitudes due to illumination constraints, and is also something like 1 kilometer per pixel resolution. So to get down to a more useful traverse scale, we want to start using full resolution M-cube data, which are available at closer to 100 meters per pixel. So due to the pole crossing orbit, M-cubed coverage for the candidate Artemis 3 regions is really good. So I'm showing the number of observations for these 13 different candidate Artemis 3 regions, the number of M-cubed observations for each regions in this table. So for some of these regions, we have over 100 observations with M-cubed data. So essentially, we're going to be able to stack this data. We're going to be able to optimize illumination across different mission phases. So we'll be able to build up really, really robust M-cubed maps for some of these candidate sites, depending on the exact number of observations we have. One issue is that we do have some significant spatial offsets from LRO data in some of the M-cubed images. So at this point, this is affecting our ability to perform reliable photometric and thermal corrections. This is a solvable problem. So a lot of this issue stems from some of the loss of pointing data on the Chandrayaan-1 spacecraft during mission operations. But recently, Eric Malloret at ACT has come up with a new way to basically reconstruct some of the M-cubed pointing data. And we recently submitted a PDAR to NASA to recalibrate this M-cubed data using this new orbital solution. And it does result in some of the initial examples. There's vastly improved calibration possible with some of this data. So if something like this gets funded in the future, it's going to significantly improve our ability to characterize some of these polar regions and do data stacking and different thermal and photometric calibrations that are really essential at these high latitudes. But we still have great data now, and we can still use it while we're waiting for some calibration improvements. So here we're looking at an M-cubed image from the Degurlash Kosher Massif region. As we mentioned earlier, this is one of the regions that's closest to the South Pole Aitken Basin. So this would be a good candidate region to go to give yourself a higher than average chance of collecting South Pole Aitken Basin material in the Artemis exploration zone. So on the left here, we're showing elevation from Lola, and on the right is an M-cubed parameter map. So like we've just been discussing, illumination conditions at high latitudes makes performing your kind of standard spectroscopic analyses a little challenging. So typical things like doing band fits to the 1 and 2 micron absorption bands, the data is a little bit noisy. So when you're trying to fit bands with parabolas or Gaussians or things like that, they can behave in pretty unpredictable ways at these high latitudes. But one approach we found to be really effective is PCA deconvolution. And so what this does is that it essentially takes the 85 channel M-cubed image, and it tries, and basically using mathematical transformations, it restructures that 85 channel image in a way that the primary modes of spectroscopic variation are captured in a relatively small number of output bands. And when you plot some of those individual bands, you can get some really interesting results that show you kind of maps of the primary modes of spectral variation across the image. So these PCA bands are not necessarily linked to any specific physical or spectroscopic property, but they do show you kind of spatially coherent ways of where spectra are unique. So here we're showing a map of PCA band 5 for this M-cubed image identifier that's listed here. And so in this very specific case, PCA band 5 for this image has ended up being very well correlated with a pyroxene-like spectral signature. And we're seeing it show up in two specific types of areas. So the red arrows here are indicating small, fresh craters. So this is an example of one here. So these are like 300 meters across. You can see in this NAC frame that you have some boulders and other various things on the rim and proximal ejecta of those craters. So these are fairly small, fresh craters that are exhibiting this pyroxene-like signature we see in the PCA band map. We also see similar signatures showing up in illuminated slopes. So those are indicated by the white arrows. Yeah, so again, these two red arrows are showing two small fresh impact craters. They're about 300 meters across. And we've got oblique NAC frames of those here. You maybe can make out that there's some boulders in the walls and rims and ejecta of these craters. But the other thing I'm showing in this slide is a comparison of the full resolution M-cube data to the resolution of the Kagoya iron abundance map. Essentially, this is just showing that we really do need this full resolution data to be able to kind of design and optimize any traverse planning and science optimization at the surface. Okay, so in addition to this spatial information, so this M-cube data can also provide detailed compositional information or mineralogical information that helps us understand the nature of these lithologies we've identified at the surface and put them into spatial context. So here we're showing the spectra of those two different pyroxene-like lithologies we identified with the PCA deconvolution. So the purple spectra are the spectra of the small fresh craters, and the pink spectra are the spectra of the illuminated slopes. So both of these units have pyroxene-like spectra, but they do look a little bit different. So why am I using the term pyroxene-like? Okay, so to investigate the composition of these a little bit further, what we can do is look at the center of the 1 and 2 micron absorption bands. So generally, pyroxene-bearing materials exhibit a very systematic relationship between the wavelength positions of the 1 and 2 micron absorption bands. So these band centers vary in concert with changing iron, calcium, and magnesium content. So generally, magnesium-rich, low calcium pyroxenes, they exhibit short wavelength absorption bands. And as you move to more iron and calcium-rich kleiner pyroxenes, like those found in Mare basalts, those exhibit longer wavelength absorption bands. So when we plot up the 1 versus 2 micron absorption band relationship for the small fresh craters, we see that these are plotting squarely within this low calcium pyroxene zone. And we see that it plots right among the population of low calcium pyroxene bearing materials from elsewhere in SPA. So these are things like crater central peaks, crater rims and walls, some larger basin structures. So these look very much like other norites we see around SPA. But interestingly, these craters do not resemble the more iron and calcium rich pyroxenes that we're seeing associated with the thorium-bearing materials, particularly in Northwest SPA. So these two particular small craters might not be the best targets to sample some of this late-stage lunar magma ocean material that was excavated by SPA. So getting back to this term pyroxene-like, so on the other hand, the illuminated slope spectra are plotting way down here. They're way off this expected trend. When we look at the spectra, they're not particularly noisy. So I think we're measuring the band centers okay. So there's nothing to do with the SNR here. So there's something happening where there's either an inappropriate photometric or thermal correction that are affecting these spectra. Something is sending this band center relationship way off the chart, and we don't quite understand what that is. So is this an observation artifact, or is this a real property of the reflectance spectrum of this material on the surface? So there's a few ways we want to follow up with this. If this is a real signature of the surface, this is really interesting because we haven't seen this particular set of absorption band properties before. So ways we can follow up on this. So either improved calibration of the M-cube data, which can resolve some of those photometric and thermal issues like we discussed earlier. Or the other thing is actually launching today, Trailblazer. We'll be able to image some of these same spots and give us a sense with an entirely different signal chain as to whether we're seeing the same thing happening on the surface with different instruments. We can also go look at things like the spectral profiler data, but again, that's going to be a little more difficult because the spatial resolution is a little lower, but we might be able to coax something out. Okay. So to conclude this part, we have a few composition-related conclusions. So Artemis will sample diverse crustal materials and Basin ejecta, which will provide critical new insight into lunar evolution. We've integrated several compositional remote sensing data sets, including Lunar Prospector, Kaguya Spectral Profiler, and Moon Mineralogy Mapper hyperspectral data. And this data provides key context for establishing some of our sample return goals, and also context for interpreting some of the samples once we do get them back. Generally, the south pole of the moon exhibits an enhanced mafic bearing signature that's likely related to dispersed and diluted, but non-zero SPA ejecta. So we should be able to sample some of this material at the south pole. And M-cubed is particularly useful because we can use it to identify small-scale mafic anomalies, such as small fresh craters, steep slopes, and other types of geologic features that might be host to some of these high-priority samples. And then we did see that some of these small mafic craters that we identified near the de Gerlache-Kosher Massif region, they exhibit a pronounced pyroxene signature, but it is a low calcium pyroxene bearing signature. So they're not similar to the high calcium pyroxene thorium bearing materials that we see elsewhere in SPA. Okay. So the other thing I wanted to take a quick look at was some of the accessibility of some of these high priority sample sites. And we do this by looking at example traverses. So one thing I've been working on in some of my support of the Artemis campaign, as well as in support of some of these science efforts, is designing traverses across the lunar surface. So here what we're looking at is a notional science traverse from a well-illuminated point within the de Gerlache-Kosher Massif candidate landing region. So that's this point here. And I've designed a traverse starting at this well-illuminated point within the region and going out to the two example craters that have that pronounced pyroxene signature. So what would a traverse here look like? So to construct the traverse, we use the least cost path tool in ArcMap. So we have a few different inputs to this tool. And what we do is we first assemble a blended cost raster. And so what this cost raster does is it takes different environmental properties and assigns a specific cost to those or a specific cost scale. And then you can use, so in that way you can assemble essentially a stack of different environmental properties, assign a cost scale, and then optimize a traverse path based on the parameters and the weightings you decide on. So here we are assembling a blended cost raster that integrates topographic slope. So we've assumed a certain cost scale and cost thresholds for that slope. And we've also combined that with maps of average solar illumination, because it can be helpful to, obviously, to have light for things like power generation from solar panels, as well as being able to see where you're going on the ground. That's important if you don't have your own illumination source. and also direct to Earth visibility. So depending on what sorts of communications assets we have on the lunar surface or in orbit, it may be more or less helpful to have direct to Earth visibility for communications purposes. So the exact cost functions that we're applying to these different environmental properties is very much an open question. So this is something we're actively exploring and iterating on, because obviously the exact cost functions you apply to these different environmental properties will give you very different output traverses depending on how steep or shallow your cost functions are. The other thing is we're experimenting with other environmental properties as well. So you could incorporate things like minimum, maximum surface temperature, visibility to other potential surface assets, communications assets, power assets. You can establish keep out zones. Say you have a reactor on the surface that you need to maintain a certain distance from. If there are keep out zones for communications beams, things like that. So you can use this tool in a lot of different powerful ways to optimize traverses. But essentially, when we feed all this data into the model, it cranks out optimized traverses, and you can see, how these different traverses trace the surface and try to minimize slopes that you encounter, and to maximize things like illumination and direct to Earth visibility. So once we derive these traverses, we can do things like extract elevation profiles to calculate things like directional slopes, and look at other profiles to understand the types of environmental conditions that you'll be encountering along the traverse path. So for instance, you can see what your average solar illumination is. And as an example, along this science traverse out to these mafic craters, your average illumination varies from something like solar illumination from 60 or 70% of the time, getting as low as 20% of the time. So when you have information like this, you can understand where are good areas to kind of sit and rest that have maybe more of a positive or more of a favorable illumination environment, and areas that you need to get through either very quickly or at very specific times that are in illumination for only very short windows. So yeah, you can really use these tools to plan out not only traverse paths but traverse timing. And yeah, you can identify areas where you might drop out of direct to Earth visibility. So, these are potential comms blackout zones if you don't have other comms assets on the surface or in orbit. You can also do things like understand the types of slopes you're dealing with along the traverse. So whether those slopes are positive, are you going uphill, or negative, you're going downhill. You can understand the magnitude of those slopes to understand the types of the energy consumption that you'll be using in your vehicle at different times. And then where this tool gets really powerful is understanding, okay, if we need to stop and charge with solar panels because we've used a ton of energy going uphill here, we want to make sure that there's an area nearby where we have a favorable illumination spot that we can kind of sit in and recharge our panels. And of course, all these illumination conditions will vary year to year and month to month. So running these models within specific time windows is really important to understand what the average illumination looks like over a specific window that you might be traversing in. Here we're using an average over a long time frame. But if you were going to set out on a traverse at a very specific time, you would want to run an illumination model for the actual window, the actual time window you're traversing in. Okay, so that pretty much sums up what I wanted to chat about today. Thank you very much for your time, and very happy to take any questions. Thank you.
Well, thank you so much, Dan. And yeah, we'll open this stuff up to questions. Let's see in the chat here. And as well. Okay, so do we have any questions? Oh, yeah, there we go. So from Donald, we have, has the Traverse tool used been vetted / compared to random and similar resolution test locations on Earth? Traveling in the field is always more difficult when trail breaking occurs than initially expected, and that's without needing to carry your air with you.
Yep, absolutely. So one of the big challenges with this tool is, understanding how the data changes as you go from the orbital scale to the traverse scale. So when we're looking at traverses right at the South Pole, we have LOLA data at 5 meters per pixel. This is a product that's been published by the LOLA team, so that's publicly available. We're also starting to get 1 or 2 meter per pixel products, which are possible through things like shape from shading models from LROC NAC data. We have some of that data for some of the Apollo landing sites. So I think Apollo 17, that data exists and is published. So you can get pretty high resolution topography. Again, going down to like 1 or 2 meters per pixel resolution. And then we're also working on the next generation of lunar orbiters. So at Goddard, we're working on the LEXO spacecraft. And the requirement for the high resolution imager on that spacecraft is to resolve features that are about a quarter of a meter in size. So eventually with an instrument like that, we'll be able to get topographic data at the 25 centimeter per pixel range. So at that scale, we're really going to be resolving pretty much everything you have to worry about during a traverse. Anything that's in your way, we'll be able to see. So a lot of those bumps and wiggles will be taken care of when we have that really high resolution data from the next generation of lunar orbiters. But no, I mean it's a really good point. Like when you go from so the data we're using here, the topography data is 10 meters per pixel. So obviously, if you go that limits the size of the bumps and wiggles resulting from features in that 10 meter per pixel data. The other important point about this LOLA data is that it comes from a laser altimeter. So we're looking at point sources, and there's a large number of pixels in these gridded data products that don't actually include any laser shots. And even within a pixel, even if it does have a laser shot, it could have missed features that are below the resolution of the pixel fairly easily. So you're always going to see different things on the ground than you see from orbit. And so accounting for, so if you use a tool like this to drive a traverse, which length is, let's say 10 kilometers, you want to put in some margin on that. So a 10-kilometer traverse derived from orbit is not a 10-kilometer traverse on the ground. There's a margin of 50% or 100% that you're going to want to put on that orbitally derived traverse. So hopefully that addresses the question.
And then Dan, what was the name of the Traverse tool that you guys are using?
Yep. So I'm using the least cost path tool in ArcMap. And essentially, it lets you build up a cost raster. So you can define a cost raster based on any number of input environmental rasters. So you can get as creative with it as you want in terms of what data you're including and what types of cost scales or cost weighting you're applying to that data. You basically take a sum of all these different cost rasters, and then the model will generate an optimal traverse based on the cost raster you define.
Okay, well, thank you, Donald and Carlos, for your questions. Paul is wondering, can the anomalous band centers be due to hematite contamination?
I can't speak to that. I think let's go up to the relevant slide. So these absorption bands are very specifically the result of iron-bearing minerals. So I think at this point, what we're seeing here is, I would wager, not the result of human contamination. It seems like an observation artifact, but I'm really interested to submit this as a Trailblazer target and see if they're seeing the same thing. If this is a real signature, if this is a real property of the surface material, that's interesting, and we need to find out what's causing this deviation from this normal trend. Because again, if you look at the spectra, I mean, that looks like pyroxene. This light pink spectrum looks a lot like pyroxene. It's only when you start measuring the absorption bands that it starts to look very different. So is this a property of the pyroxene itself that's weird, or is there some non-pyroxene component in the in the lithology? Or one possibility is we know from some of Shuai Li's work, there are some unusual space weathering products at high latitude, including hematite. Hematite, if you look at what hematite does, it can give you some weird kind of bumps and local maxima in this range, which could shift your bands this way. So if you have a local maximum from hematite in this like 1.2 micron range, something like that, that could potentially shift your 1 micron band short and pull you off this trend here. So maybe, and the other kind of important point that Shuai brought up is that a lot of the hematite signature they were detecting was in these sun-facing slopes, or at least some of the earth-facing slopes. So it's possible that this is the result of unusual space weathering, specifically hematite, which could potentially pull your 1 micron band center to non-physically realistic short wavelengths. So that hematite possibility is something we're looking into as well. And if Trailblazer backs it up, then that's a pretty strong piece of independent evidence that this is a real property of the surface and is probably due to something like hematite space weathering.
Well, thank you for that, Paul. Carlos is also wondering, in relation to the Traverse tool, is it able to manage dynamic planning, such as finding an optimal solution for changing illumination conditions, which would be important for the South Pole?
Yeah, that's a really good question. So the tools we're using are static. So there's no time dimension, which is why we need to use maps of average solar illumination and average Earth visibility over a specified time window. There is like a software team at NASA Johnson that's working on a time-dependent kind of traverse solving tool. And that may exist for previous missions like Viper, so it might be taking some heritage from some of those rovers. But yeah, I don't use any time-dependent layers, and actually the tool I use is not capable of supporting time-dependent layers. So yeah, we need to develop essentially purpose-built software for that approach.
Thank you for that, Carlos. Chip, you have a question?
Yeah, I sure do. Dan, thank you again for giving this presentation. This has been terrific. The question I had was, let's go ahead and leap from orbit to boots on the ground. What criteria, based on your data so far, should astronauts use in order to select samples derived from SPA? And also, what sort of criteria should they use in order to pick those samples that are best for establishing chronology?
Yep, that's a really good question. So in terms of following up on this distribution of thorium and iron-rich material, if they had some sort of hand spectrometer or field spec that was able to look at band centers, to get this thorium-bearing SPA ejecta, which is the deepest stuff ejected by SPA, and then in that sense probably was most likely to have melted, you probably want to be targeting stuff up here. So they could do this in a few different ways. There's a few different compositional properties we've identified that are good markers of this material. So high iron, high thorium, high potassium, high titanium, and then a kind of iron and calcium rich pyroxene bearing composition. So any number of instruments could get you that. If you have a gamma ray spectrometer on the surface, I'm not exactly sure of the integration times you need on those. Given that you're right in the surface, you might be able to do it pretty quickly. I know different rovers have explored the idea of having gamma ray spectrometers on the surface. So if you do have a gamma ray spectrometer and it starts pinging thorium, you should pick up that rock. If you have a field spec, if you have a hand spectrometer, and you start seeing a lot of really iron and calcium-rich pyroxenes, you are either looking at a Mare basalt or a possible piece of this late-stage lunar magma ocean cumulate ejected by SPA, and you'd want to use some context in terms of the crystallization textures and things to get a sense of that. If you have large grains and it's like a slow crystallized material, maybe that's a lunar magma ocean cumulate excavated by SPA. If it's really fine grain and looks more like an extrusive basalt, maybe you're looking at some of these high latitude basalts that we potentially saw in Ibn Baja here. So yeah, there's different ways of attacking it. So certainly compositionally, but also through some of the crystallization textures, which again may or may not be maintained after excavation from a 2,000 kilometer impact basin. So it's going to be a lot of impact breccias and things like that. But I think the idea is getting a diversity of samples should get you the answer eventually through statistics. I think the most diagnostic thing would be that thorium signature.
Well, thank you, Dan. Thank you, Chip, for the question. Do we have any final questions, comments, or concerns? All right, well, if not, guys, thank you so much for coming today for the Planetary Science Sample Seminar Series. Please join us again this time next week. We'll have Patka Main from the LPI. We'll be talking about the distribution of niobium radioisotopes in the early solar system, if I remember that correctly. So please join us again, guys, next week. Dan, once again, thank you so much.
Thank you very much. This is fun.